My name is James. I'm the bald engineer. Okay, so as I was mentioning before I went and did some troubleshooting, I have a new streaming setup, and so I think I know why the lag happened, which is actually bad news, but I'll worry about how to fix it later. So I think we'll be in better shape moving forward. If it lags again, let me know. In this live stream, I have something cool to show. Yesterday, I was at the Bay Area electronics flea market. It's something that gets held once a month for like 9 months out of the year. I almost always end up buying an old piece of test equipment, but yesterday was unique because I bought this analog oscilloscope, and when I bought it, the screen didn't work. It actually outputted nothing. And so I spent a couple of hours troubleshooting it, and I found that there was a resistor that had actually burned up. And so when I first opened up the high voltage power supply, which is basically feeding the CRT, I found that there was this capacitor, and I saw all this black junk all over it. And I thought, oh, it looks like the capacitor's wax had leaked out, because metallized polyester caps have like a wax film that goes over them, a wax layer. But then I realized up here that same black stuff was also present. And what I'm thinking has actually happened is, I think there's an actual issue. There's another issue with this scope that causes this resistor to burn out. And I think this has been repaired before. But when I cleaned this all up, this is probably the best picture. You can actually see the resistor is just totally toasted. In fact, I still have it. I don't think you're going to be able to see it, but we'll try. Yeah, I mean, it's gone. So replace that resistor, and once I did, got a working scope. So what I thought we'd do is talk about how this analog scope works. You know, I've got a function generator up here that I'll take you through. We'll put some waveforms in. I'll talk about how to use the controls and just kind of test it out. So part of this will be demoing how it works, and part of it is I'm trying to understand how to use it, because I'm not really an expert when it comes to analog scopes. I've worked with oscilloscope companies for 20 years, but I've always dealt with digital scopes. So it's kind of fun to really try to understand what's going on with this. Now, before we get into the demo, I did want to go through a couple of things that I thought were cool about the scope. And so to do that, let's go back in time to when it was new. Let's try this one. So what's really cool is companies like Tektronix and Agilent. Well, let's see, let me back up. Tektronix and HP, before they became Agilent and before they became Keysight, used to have magazines that would talk all about their products. And so what's cool about this is if there's archives on the web with these magazines, and so you can actually read, one, what was the marketing talking about in terms of these products, and then what did the engineers actually have to say about them. And so I found that, so Tech's magazine was called TechScope, HP's was the HP Journal, and so whenever I get a hold of a piece of equipment, I try to go find the magazine that talks about it. And so in this one, this TechScope, it talks about the 7704, extended performance plus modularity. So the way that this scope works out is there's actually two pieces to it. There's this section, which is the display, and then this section, which is the acquisition hardware. And in fact, on the very first page, you can tell that they think that this is a big deal because they show sort of an expanded view of what this scope would look like if you take it apart. And so, to me, this is actually, hold on. So to me, this is actually interesting because there's only a couple of screws that hold this whole chassis together, but when you pick it up, it feels solid. But you can actually see that the display unit is all by itself, and then there's these plug-in the section down here that holds the plug-in modules. And then I was also noticing that there are expansions that can go in between the two, as well as you can basically take this display unit, replace it, and get a more advanced display unit while still using the same acquisition. So I think that's actually pretty cool that it's that kind of flexibility. Can you hide the comments? Yeah, I don't actually hide the comments on the screen because I stream in multiple places and people get confused when they can't see who I'm talking to. And so I just like to leave them up. And then plus when I do like picture-in-picture, it's easier to tell where they're picture-in-picture. So sorry, comments are there for live streams. Now, reading through the article, one of the things that I thought was funny is it talks about these high-speed CRT. And so with this CRT, or what they're really talking about is, okay, hey, not only is the scope have all this amazing measurement performance, but our CRT is really fast. And it's not even so much because of what we can visually see, but if you look in here, they're talking about what happens when you use a camera to take screenshots. And in fact, up until, probably in the 90s, maybe even early 2000s, you could actually attach a camera directly onto the front of this scope and take a picture. And then they've got options in a different CRT that allows it to be better used for taking pictures of the screen. And so I think that's pretty amazing to think about, because this was like in 1972, or this was released in 1972. And here they are talking about how you take a picture of the screen, and here, fast forward to today, and screenshots are still a thing. So I think that's pretty cool. Someone is asking, is that your rack mount? Some had that form factor. Or is yours a rack mount? Offhand, I don't know. For equipment in this era, I don't know if there were standard rack mount sizes or not, so I can't really answer that. But this particular unit has no, I don't see where you would actually attach a rack mount kit to it. The other thing I thought was interesting, they talked a lot about the power supply, and I wish I could, I wish I had the picture. What's really cool is the power supply unit is designed so that you can actually pull the power supply out and work on the power supply while the scope is powered. The cables are actually extended far enough that it can actually sit outside of the box. I just think that's pretty amazing. The other reason I just thought talking about the power supply was funny is, in a modern instrument, how often would somebody talk about, oh, we have a high efficiency power supply? But 40 years ago, that wasn't the case. Now, the next thing is it talks about this front panel focus control, and that the scope has what they call autofocus. And we might see it today. There's actually a problem with my autofocus circuit. It's not working exactly how I would expect. But basically what happens on an analog scope, as you start changing some of the parameters, and of course now it's not going to do it, the way that the screen is getting drawn, it starts to literally lose focus and get kind of blurry. And so they have a circuit in this one that actually monitors the brightness or intensity and tries to modify the focus along with it. And so I just think it's interesting what was important at the time that this oscilloscope entered the market. And then I thought I had one more point I was going to make. Maybe that was the last one. Oh, CRT readout. Now, it's going to be difficult for you to see on camera. Sorry, I ran out of cameras, so I can't really zoom in. But I think you can at least see there's something here and something up here. And what it is, this scope actually has what this feature calls CRT readout. Oh, you couldn't even see that. It has what's called CRT readout. And so it's actually showing the time base as a number. So I can see it's currently set to 200 nanoseconds. And down here, the vertical is at greater than 100 millivolts per division. And the reason it's a greater than is because I have it on vernier. Now, if you've used a modern scope, that's not a big deal. Every digital scope has that information on screen. But 40 years ago, it was really common to just have a waveform. And so if you're taking screenshots, you had no way of knowing what any of the settings were, you couldn't actually make a measurement. So by adding a readout, it makes it possible to actually see what's going on. So, okay. I'm not really good with names, so I'm just going to say, so high efficiency supply. I don't know if they actually said the number in here. They really just kind of go into the idea that there's an IC that's basically a PMIC, a power management integrated controller, and which back in the 40s didn't exist yet. And then they talk a lot about how, I'm not going to find it right now, but there's a section in here where it talks about in the case of a fault, the supply doesn't just shut down, it goes into a pulse mode so that the operator can find the problem. Now, I said now, but one thing, I meant to mention this at the beginning. My goal is I want to do a full video, an edited video on this scope. And in that one, I show where I take it apart. This is one of the easiest pieces of equipment I've ever worked on. The panels have a really easy screw system. It's just a locking screw. It's not threaded. So all the panels come off. And then once they come off, there's individual circuit boards inside, and each circuit board is clearly identified to what it does, which I really appreciate that, because it's like, wow, I can see so like over here is the vertical amplifier, back there is, in the very back is the Z-axis controller, blah, blah, blah. Anyway, I think that's really cool. Let me catch up on chat messages, and then we're going to go on to other things. And then we're going to get into actually making measurements. So, thanks for the follow. MediModern LXI compatible today, support a screenshot feature via the network. Yep. Yeah. There's, I was going to make a comment about modern screenshots, and then I wanted to hold back. So in even in today's world, so I work for a test and measurement company that makes oscilloscopes, not these guys. And every once in a while, I still get customers that will send me a screenshot from their phone of their scope, even though every one of our scopes has a button to create a screenshot. And it just kind of cracks me up that even though scopes can save their own screen, people still take pictures. Story time. When I was in college, digital scopes were just becoming popular, and we had a Tech TDS something, which had a floppy drive. And at first I thought, this is great for lab reports. I can just throw in a floppy drive, hit save screen, and then it spit out like a bitmap or something. The problem is it took 1 minute and 30 seconds to save it. So we ended up just using a Polaroid most of the time. Okay. Let's see. Bosch scope. Ooh, I would love to see a Bosch scope. Rack mounts. So if rack mounts stayed standard for 40 years at the 19-inch, then this would definitely need a kit, and I'm not sure if there's a kit available. And then what did you pay for this scope? Oh. Well, so here's the story. So I was looking at it, I took a picture of it, threw it on Instagram, and I was just kind of joking, hey, this looks really nice. I mean, the scope is in really good condition. And then the guy walks over and he says, well, I want $125 for it. And I was like, oh, that's a pretty good price, but I promised myself I wasn't going to buy a scope because I've got too many. And so I started to walk away, and then I thought, even if it doesn't work, it looks really good. So I'll go ahead and take it. So I walked back over, and he said, tell you what, $100 because the screen doesn't work. And I'm like, oh, I'm going to have to fix it. So I paid $100, and then I had to go to Fry's and buy resistors. So the resistors cost me $1.50. So I paid $101.50. So I think I got a pretty good deal. Okay, enough of that. Let's go talk about the scope. Let me drink some tea first. Says, boy, are they flame-proof resistors? Yes, they are, in fact. Okay. So, can we... maybe that look a little better. So the way just backing up real quick, so the way an oscilloscope works is across the horizontal axis is time, and across the vertical is voltage. And so we're looking at voltage across time, and as you can see, I'm looking at a sine wave here. So the way that a analog scope works is the screen is being drawn by the electron gun. And so the idea is there is a single dot, let's go to ground. There is a single dot that's sweeping across the screen. And so as it sweeps across the screen, the vertical channels, which are sometimes the vertical amplifiers, they have a vertical amplifier that deflects the electron beam. And so as the beam sweeps across, the vertical channel causes it to deflect, which is how we end up with a waveform. Now, this scope, even though it's 40 years old, the screen is a little more advanced than that. It's using a different type of sweeping technology, partially because it has to do things like paint the raster, or I think they call it a raster unit. Paint the raster of the readout, and so it's not as simple as even a simpler analog scope that literally is just an electron beam sweeping across. But conceptually, that's what's going on. So with the vertical module, that allows us to get the voltage, and then the time-based modules allow us to alter how our sweep occurs. Okay, hold on. Let's just do a quick, let's just do ban and done. Okay, so let's see. Let me back up. Gotta love trolls. Okay, so totally lost my train of thought. Now let me back up. So we've talked about is horizontal is time, vertical is voltage. Now let's talk about what's unique to this specific scope. So there are 4 modules, and just to demonstrate, I'm going to pull one of these out. And so they're just these nice, cool, slender looking things, and inside is a whole bunch of stuff to make them work. Now, this looks like it's ultra flexible, but it's really just that it's modular, because there are two vertical slots, and then a delay time base and a normal time base. And so to be a functional scope or usable scope, you have to have at least one vertical channel or one vertical module, and then a triggering module, so that you can actually trigger when the electron beam starts to sweep across. And so let's see, sweep across. I forgot I turned it off, and I was like, why did my screen stop? Anyway, now the way that these channels work, I can change the volts per division, which changes the size of the waveform. And then over here on the time base, I can change I'm using this time base. I can change how long does it take to sweep across, so we can see different frequencies. Now you might see all of these buttons and all these lights, and so what's going on with all this stuff? So this is for vertical, this is for horizontal, and basically it's what do I select for the instrument to use? So right now I'm I'm using the left module. We could also look at the right module. And then in terms of trigger source, and so in an analog scope, the trigger is when the electron beam starts back at the left side. Which module do I want to use to trigger the scope? And so for all intents and purposes, we could use either one to trigger this particular scope, and I'll explain a little bit what's the difference between these two. So we get our vertical sensitivity and then our horizontal time base. Let's see, what else can we talk about? What are all these knobs going on? So this is 2 channels, and for no obvious reason, I'm hooked up to channel 2. So this is the volts per division for channel 2. This knob allows me to tell the scope, okay, I want to trigger on either channel 1 or channel 2. So that signal then gets fed over to the trigger module, and then the trigger module looks for the signal to either to have a rising or falling edge at 0 volt. I think at 0 volts. And in fact, if we change this guy, it'll change. So I can't remember now. So this is rising edge, and I think this is falling edge. So we can actually tell the scope, do I want the trigger to come from which channel? Right now it's on channel 2. And then what's the delay mode? So if we want to look at both of these channels at the same time, then we have to actually use a chop or alternate waveform view. And so what this allows me to do now is, let's put this one down here, and let's put this one up here. So this beam is channel 1, which has nothing connected to it, and this beam is channel 2. And so this module can combine 2 channels on the scope at one time. But then, uh-oh, that won't work. Does that not work? Uh-oh. Okay, I was expecting, okay. I was expecting, okay, so Alt and Chop allow us to switch between this module and this module, and I'm not sure why I lost my trigger when I did that. So we're not going to do that for now. How does the horizontal time base for a single channel work? I'm not sure I understand that question because I'm actually only looking at a single channel at the moment. But in general, the time base is tied to, or both or all vertical channels are tied to this single time base. However, there's an exception to that, and I'll come back to that. So okay, so what were we doing? So that's how we had. So we had that going on. Okay, now what I want to do is let's go pulse. So we got a pulse happening. Do a single channel. I'm going to zoom out. All right, and move this up here. So notice as I change my position, I lose my trigger. Let's see if we can get the intensity up a little bit. Hold on, I just realized. So I'm looking at the screen from an angle, and to me it looks straight, but I just looked on the monitor and I can see that it's actually not straight. Okay, that looks a lot better. So we've got this signal going on. I should have done it this way. So I'm going to use the delay time base. So let's talk a little bit about what the delay time base does. So the delay time base allows us to basically trigger the scope twice, which is not necessarily what's going on, but that's how I think of it in terms of an analog scope. So here we are, I've got a pulse coming out of my pulse generator, and we can see the pulse happens, and then there's a whole lot of activity, but it's a little bit more difficult to see what's going on because we've got a lot of activity happening. So what if I wanted to just look at one of these pulses? That's where I can go into my delay mode. Now I gotta think for a second. How do you turn that back on? I do the chop. Yep, okay. So overall, my trigger selection, I can either use trigger module A or B. I'm going to say, or do I want to do alt? Yeah, I want to do alternate. So it's going to trigger. So, well, it's going to alternate. So we're actually getting 2 sweeps of the screen at a time. Are you a salesman for a scope company, so you might know prices and not much more? Well, that's kind of rude. I'm just going to ignore that question. Let's see. Now, I'm going to increase the intensity so we can actually see it. And let's see what you guys are seeing. Yep. So what's interesting about this is I'm basically able to sweep through this waveform and see what's going on through time. And so that's where this idea of a delayed time base comes from. So up here we have the original waveform that's triggering the scope, and then what it basically does is generate another trigger, or generates another trigger signal, so that we can then see that same waveform but in a more expanded time base. The problem with that is, if you notice, this waveform starts to get really fuzzy, and the reason is it's actually getting painted twice. So it's cool because we can zoom in on a waveform, but it's got some trade-offs. I think it's pretty cool because this is something that's been in scopes for now 40 years. I mean, this is something you do in a digital scope all the time. You basically capture the waveform, do a zoom window, and then take a look at what are the details going on. It didn't occur to me that a 40-year-old scope could actually do that. And so I think that's pretty cool. All right, let's go back to here, get this going, see our waveform again, and expand. Okay, so at that point, I'm going to pause because to see if there's any questions, and then I've got an experiment I haven't tried at all that I want to try next to see how the analog performance of the scope actually works. In fact, we're going to start getting that set up right now. Well, let's see, turn this guy off, turn the intensity down while I do this. I'm basically going to swap out my function generator with my spectrum analyzer. And you might think, well, wait a minute, how does a spectrum analyzer help us? You use a spectrum analyzer to look at signals. That is a true statement. However, this spectrum analyzer also has a RF generator. And so the spec for this module is it is a 200 megahertz channel or amplifier. My function generator can only output 20 megahertz. And so we are going to use my spectrum analyzer's generator to get a signal from about, I think, 10 kilohertz up to 200 megahertz just to see how it actually works. So I'm going to get that set up and going. Does it have a GPIB interface? Okay. At first, I thought that might be, I sort of thought, that's kind of a silly question, because I thought the same thing. And then I thought to myself, how would it? There is a module you can get, which then I think you break this apart, you put in the programmable module and then connect them together. And it can do some GPIB stuff, but the thing to remember is with a lot of these instruments like this one, these knobs are directly controlling stuff inside the instrument. So this potentiometer is live. It's not just a control and separate it from the control hardware. And so, something like this, it'd be really difficult to do a lot of remote programmability simply because you have to have somebody turn the knob. I did not want to plug that in yet because I want it to come up to, so you can see what I'm doing. Let's try this. Mode, no, where's it at? Measure, source, CW, and then level. I'm pretty sure I want it to go down that way. Okay. So now we'll plug this in, change the channel to channel 1, and then we need to change our frequency to, let's go 1 megahertz. Okay. Don't see anything yet, and we're not triggering. I am going to use the other trigger module. Okay, so now it's starting to trigger. Let's go. Okay, now we're getting somewhere. All right, and then, oh, I know what's going on. It's not finding the trigger or the trigger point. All right, so let's increase the output of this guy to -20 dBm. That's looking a little better, maybe? Nope. Can I get the level now? I think maybe we're... No. Okay, let me think. I'm DC. Do I want to be AC coupled for this? Maybe I do want to do AC coupling. Because I don't... I mean, this shouldn't be putting out a DC offset. Source internal hold off. I'm missing something. What am I missing? Let's think. So let's think. I'm putting out a 1 megahertz sine wave. So that should be 1 microsecond. So if I want to see one cycle, it'd be 100 nanoseconds per division. So let's go there. So we're almost there. So I really think what's going on is the scope's not finding the trigger level. And if that's the case, I'm not sure what to do, because it should be right at the 0 point. Unless, does this channel have a... Oh my God. You need to train your thought process to teach less educated with much furring and backtracking in your commentary because it's confusing and irritating. All right. Well, I don't know what to tell you. As I said at the beginning, and maybe you weren't here, so I'll give you the benefit of the doubt. This is part demo and part me playing around with the instrument while I try to figure out how it works. If you find that frustrating, hey, no problem, friend. Later on, I'll put out an edited video that'll be nice and clean, and you're welcome to come back and provide trolling comments then. So, okay. The thing that I can't believe this. Why this outputs a square wave? Huh. I would have thought that would be a sine wave. Anyway, let's see. We're at 200 nanoseconds per division. Like I said, if I go back to 100 nanoseconds per division, and then let's change our... Yep, so 1 megahertz. Quick Bald Engineer oscilloscope math. When I was playing with this last night, I really wish it had a frequency measurement. Okay, now what I want to do, let's see, how can we do this? It'd be really nice if I could take a screenshot. I'm going to center this. Basically, there is a 1090 marker on my grid, and I know you're not going to be able to see that, but I can. But what I want to basically watch is, as I increase the frequency on the generator, how does the amplitude change? And so let's go to frequency. How much is that? Oh, that's going to be painful. So 2 megahertz, I would expect it to be about the same. Go to 10 megahertz. That's looking about the same. Let's go to 50 megahertz. And the amplitude looks like it got bigger, but I think what's going on is there's some ringing, because this is 50 ohms out going into 1 mega ohm. And at 50 megahertz, we're starting to get the waveform is rounded off. Now, you might think that it's a bandwidth limit of the scope, but it's actually just that, well, wait. That might be the bandwidth limit of the scope. I'm not going to say what I was about to say. nope, that was supposed to be 100 megahertz. Okay, and so I can actually see the amplitude has reduced. So let me grab something I can use to point, and you can see, oh, this will work. So before, we were up to about here where you can't really see it because of my logo. So we're about up to here, and then we came down to about here. So I can see the amplitude is being reduced. And so there's a couple of reasons why that's occurring. As we approach the bandwidth limit of this measurement module, there we go. As we approach the bandwidth limit of this measurement module, we're dropping off some of the high frequency content in the signal, and so that naturally causes the amplitude to reduce. And so if I hit 200 megahertz, now we're at the rated limit for this module, and I would say we've lost one complete division, plus one division on the top and bottom of the waveform. And so what is that? 1, 2, 3, 4, 5, 6, 7, 8. So 6 divided by 8 is how much? 75%. I just wanted to double check. So we've lost about 30% of the incoming signal. So that's important because whenever you talk about scopes and bandwidth, we talk about the negative 3 dB point, and the 3 dB point is where you lose 10%? Oh crap, now I forgot. No, it's 30%, isn't it? Yeah. Okay, I'm gonna skip that explanation because the numbers, I think it's 30%. Anyway, as we approach the bandwidth limit, the amplitude is going down. What I'm actually surprised, okay, backing up, what I was actually looking for is at 50 megahertz, it stays about the same amplitude as at 10 megahertz. And that really surprises me that it's not until we get to the actual bandwidth limit that the amplitude is starting to reduce. So now what I want to do is see how much reduction can we get if I keep going. So let's go to 210 megahertz. Okay, it's going down to 20 megahertz. All right, 250 megahertz. Interesting. It's about 60% of the original. I'm just going to go all the way to 300 megahertz. And at 300 megahertz, we're not able to trigger anymore. And that's probably a real limit of the hardware because this frame is only rated for 250 megahertz. And now it's not triggering at all. Did I change something? Yeah, so it looks like it really is a 250 megahertz frame. 3 dB is 50% of power, or 0.7 volts. I thought oh, okay. I got confused. I was getting voltage and power confused. You're right. You lose 30% of the voltage, but it's 50% of the power. Okay. I don't know why I messed that up. Is there a significant use of an analog scope in a hobbyist lab? You know, I think the way I'm going to answer that is if you have a small budget and you have a choice between a $100 analog scope and a $100 digital scope, that is a case where I would probably consider the analog scope over the digital. If it's a case of a used digital scope, I would absolutely prefer to have the analog scope. Even though this particular scope has a few ICs in it that are specific to this scope, they're basically ASICs, or ASIC is a heavy term for it. There's custom transistors in this scope, or custom amplifiers in this scope, that you have to be able to source original parts in order to use it. However, there's only a handful of those, and those for a particular scope might be prone to failure, but in general, it's going to be the capacitors or the resistors or even the discrete transistors that fail. And so scopes like this are extremely well documented. Let me just show over here what I mean by that. Let's see, diagrams. So the service manual for this scope contains all of the schematics and and diagrams showing off all of the boards. And so being able to repair the scope is relatively easy because I have all the information I need to repair it. The problem with a used digital scope is if one of the ASICs, like the ADC or the preamp or the memory controller, go out, you can only source those 3 components from one place, and they're pretty hard to find other than just buying another scope. So for that perspective, does an analog scope have a use in a hobbyist lab? If you're budget limited and all you can afford is a used analog scope, I think there's a use for them. This is 200 megahertz. I mean, if you go buy one of those Regal discount specials that are like $350, it's like a 100 megahertz scope. Yeah, I know you can unlock higher bandwidth, but it's roughly the same bandwidth as this, so you'll be able to see the same kinds of signals. You won't be able to do cool stuff like serial triggering or decode or things like that, but if I just need to look at signals on a board, a $100 analog scope is going to be a good way to go. Now, I would caution you, if it's the first scope you're buying, that you buy one that works and don't buy one that doesn't work, because in order to fix a scope, you almost always have to have a scope to figure out how to fix it. So, an analog scope from secondhand is a good starting point for a hobbyist. Yeah, I think that's about the only use I can think of as for an analog scope, is it teaches you how to use a digital. In terms of functionality, productivity, ease of use, I would prefer digital scopes. But like I said, if I'm going to buy a digital scope, I would prefer to buy a new one. I would not trust a used scope unless I trusted the seller and knew that it was treated well and was not damaged, because repairing a digital scope is very difficult. Now, I just want to point out, that's not to say that you can always repair an analog scope. Like I mentioned, there are custom transistors or amplifiers in this scope that if it fails, I'm going to have a hard time replacing. Okay. All right. What was the next thing I want to try? Am I an electrical engineer? I have an electrical engineering degree. I went to an engineering school for electrical engineering. The reason I don't like to say the only reason I answered it that way is I only do engineering work for consulting, and so I don't necessarily like to think of myself as some other types of engineers that are out there. Any of you guys use a Picoscope 3000 series? I will definitely allow others to chime in. I haven't used the 3000. I don't even know. I think I have a 2000. Yeah. So actually I have a 2000, which is like, these are like, it's a 15 megahertz, but it starts at $150. And so it's a pretty good scope, but it's really bandwidth limited. So if I had my choice between the Picoscope or this, I'd rather have the analog scope, just because it's higher bandwidth and it looks a hell of a lot cooler. So, okay. I wanted to go through how does the screen work, what are the modules, I showed the modules, and then I wanted to hook up my generator to see what it would look like when we put high frequency into it. And so even though this is a 250 megahertz module, it was actually able to handle up to 200 megahertz module. It's displaying 250 megahertz, though at a reduced amplitude, like we would expect. Cool. All right. I wonder, I got one more thing I want to try. I was thinking about this last night, and I haven't set this up, but that's okay. We'll get this set up now. I'm going to take an Arduino, and then I need a power cable. Okay, we'll do that too. Need a power cable, and I need a USB-A cable. And then I'll explain what I'm doing here in just a second. Let's use, I don't really want to use a modern one, but I guess we will. Get a probe. Oh, yeah, actually I need this probe because I need to use my ground spring. All right. So what we're going to do is I'm going to grab my Arduino Uno, totally modern device, and we're going to make a couple of measurements on this scope with it. The last edited video I posted was using my Rohde & Schwarz scope to do something similar. So we'll do a couple measurements just to see what it would look like if we look at something other than a generator. And in fact, let me turn this off and get this guy out of the way. Okay, and so now we're going to plug our scope probe. Onto the channel. All right, I'm going to take these guys off and replace it with a little ground pin thingy. And then the reason I'm putting on this little ground pin, let's see, where's a better way for you to see it? Maybe over here. Is I'm going to probe onto the, what do I want to probe? Oh, so I'm going to probe the ceramic resonator that is like in here, which is the clock for this Arduino. So let's plug that in. Put that over there. And I'm going to plug this into here so that it has power. And then we're going to take a pause, and I'm going to ask you a question. In this setup that I'm about to do, I almost am going to make a huge mistake, and I wonder if anyone knows what that is. And okay, I'll just get this and then I'll repeat my question. Okay, so I have my Arduino board, which is USB connected to my laptop, and then I have a probe connected to my scope. And I'm going to take my probe and go poking around on my circuit. I have made a critical mistake. Does anyone know what that mistake is? That's right, Max. Mains ground. So it actually turns out EEV blog did a really good explanation on why you need to be careful about the measurements you make, because there are unintended ground loops when you connect to things, when you measure something that's connected to earth ground. So my scope is connected to earth ground, and my laptop is connected to earth ground. And so if I go start poking around, it's actually possible to create a fault condition. So to solve that, oh yeah, I can do this. We are going to disconnect my laptop so that it is floating and see if it upsets any of the streaming stuff. No, but it did upset this. Let me make a quick change. Keep that change. Minimize that. Max, been there, smoked the laptop to show. Yeah, actually in my last scope video, I feel really bad because I never mentioned that, I didn't explicitly mention that my scope was floating, and so it looked like I was making a critical mistake. I just didn't even think to say something about it. But yeah, whenever you want to measure something, say like an Arduino, if you're connected to USB, it's best to do it from a laptop and disconnect the laptop from earth mains. So now the idea is, as I touch this down, my reference will become earth, but it'll be through the instrument. Now, some people, what they'll do is they'll float the scope, which means they'll connect it to a transformer so that it's disconnected from earth ground, which I absolutely do not recommend. Instead, you should connect whatever your device under test is to the isolation transformer so that you're protected through the scope. It's always funny to me when people want to do the protection through the device under test, because if you were confident that your device was working okay, you wouldn't be testing it. So instead, keep your earth connected to the test equipment. Anyway, now we're going to go and see if we can make a measurement. I'm pretty sure I'm going to keep that AC coupled and see if that'll work. How did I do this before? Pretty sure ground is here, and that is my signal. So I need to do a little bit of math. What is 1 over 16 megahertz? Where did my phone go? Uh-oh. Does this one have it? I want to calculate the time base, and I can't do the math in my head. So what I need is, so we're looking at 16 megahertz, which should be like 1 over, so 62.5 nanoseconds. And then I want, so that's what I want my total sweep time to be. So then I need to divide it by, I think it's 10 divisions. 1, 2, 3, 4, 5. Yep, 10 divisions. So we need to be around 6.25 nanoseconds. So we'll do 5 nanoseconds. And that should get us a one cycle of the clock waveform. So let's see if it does. Oh, okay, so I'm just having a hard time getting on my ground pin here. Let's try this one. Bend this up a little bit more. That's pretty close. Let's go. I don't think I have ground. I think that is coupled. Nope, that is definitely not it. Come on. You know what we're going to have to do, because I don't remember. I've done this measurement before, but I don't remember where the ground pin is. So let's do. So you've been there, done that, smoked through. If you use a USB scope connected to a PC, what do you do then? Isolate the what do you do then? Isolate the scope. Well, if you're using a USB PC scope connected to a PC, you would still use an isolation transformer on the device under test. If you're using a USB-based scope connected to a PC and your Arduino is connected to the PC, then you're still referenced to a single earth ground. The idea is there should only be one path to earth ground throughout the entire measurement. Okay, we need to do something. That's not what I want. Oh, I've got it disconnected. So what I'm looking up on my PC is Bald Engineer Arduino scope measurements. And then I'm going to share this. Just FYI, this is what I'm looking at. Oh, that might not go through. Hey, I just pasted a link into chat. Tell me if it shows up in your chat. DTR reset. Yeah, we'll do that one. I'm looking for Probe loading. Okay. This is weird. I thought I had a picture of exactly what I need, and I don't. Well, that's dumb. I didn't do this right. What I wanted was... That should be where we need to look. However, it doesn't... I don't think it goes this way, but we're going to try just in case. Actually, now that I do it this way, this actually feels right. I dig into here and then touch to here. No. Okay. That has a little bit of a signal. That has a little bit of a signal. I'm going to try and brute force this. Nope. One of these vias is ground. I just don't remember which one. I might have to look up the... Yeah, I thought this was going to be a lot faster. Let's see. Probe loading. You know what we're going to have to do. This is so lame. We're going to do this. We're going to go to YouTube. YouTube.com. AddOhms. And then videos. Scope basics.
On Patreon.
Hey, Patreon. Yay, okay. Now, where did let me think. PWM. And then that was that's what I'm thinking of. I actually didn't do this measurement in the video. Did I? I did. There it is.
Via on the ground plane, and then touch to the termination region.
Okay. So that is what I'm actually doing. So I'm using my probe to poke onto, it looks like I said termination resistor. Okay. Thought it was a cat. I guess it is. Oh, it's like 1 mega ohm. So, yep.
It provides a shorter path.
And then what's the via I used? It's that one. Okay. So back to the regularly scheduled program. This via that termination resistor. That's looking a little bit better. That gets us a little closer. Find a night. Man, this thing is just not. I'm going to use this other trigger. I'm starting to suspect there's a problem. But I can't go that slow. Great. All right. So then let's increase volts per division. The problem is this is divided by 10. There we go. See if I can get a cleaner. This can't just be a focus thing, right? No. Why does that look terrible? DC couple it. Position's way off. I'm very concerned about how poor that signal looks right now. Bummer. I thought that'd be a really good measurement. Yeah. It's... I'm not sure if it's because the signal's too small or if there's a problem with the trigger. So 10 nanoseconds should be enough to actually see it. So let's use the other trigger input. No. All right, and then A intensity. So it's not triggered at the moment. There we go. Yeah, I'm starting to suspect that there's something wrong with my trigger module because every time I've used it so far, it's been pretty poor. So we're getting something at 200 nanoseconds per division. So let me try that just to see if the signal quality looks better. Yeah, maybe it's just at the slower time base, or maybe I just moved my hand. Anyway, all right. Let's no, that should not be AC. Oh man. Oh gosh. Okay. Okay. Oh, it is. There is something wrong. I like tapped something over here. Oh, that's not good. Okay. Wow. Oh, really? Is that what it is? Huh. Okay. So clearly there's a loose connection somewhere. I'm not sure what's going on at this point, but that's okay. We've got a stable waveform, and if we look at this, so at 20 nanoseconds per division, so if we start here, we can count 1, 2, 3, so 20 or 0, 20, 40, 60 nanoseconds, and I bet if we do the math, 60 nanoseconds is, well, I know what the number is, but we'll do the math anyway. So 60 nanoseconds, 1 over 16 megahertz. Cool, right? And I know that the Arduino is running at 16 megahertz. So that's pretty cool. Let's try one more thought. And let's just see if this is even an option. So now what we're going to do is I need to plug into pins 1 and 2. And connect. Okay, we don't need the ground tip anymore. Oh, you know what I should have? Well, we'll talk about that here in a second. This will be the transmit pin. I can disconnect that for the moment. And then I need a ground. This looks like a good place to get ground. That is not a good place to get ground. What do I need? I need a wire. Let me grab, let's see. I need a jumper wire so that I can get to my ground connection. Not sure what's going on at the moment. Yeah, there we go. So we're going to do this. Grab this. This is a terrible idea. Let's see. I'm trying to think. If you look, so here's what I've got going on. I've got this ridiculously long ground connection, and then I'm clipping this onto pin 1. Don't ever do it this way. This is terrible. This is like the worst way possible to make a measurement. Here's what I don't understand. Why don't scope probes come with something like some kind of better clip than an alligator clip for ground? I wish it would come with like a pin header to plug into stuff. I'm leaving the scope disconnected for the moment because I want to go and do some code, and that means I need to connect my computer back to there. Let's see if Sublime is working. Arduino. Let's go to Arduino thought there was a new sketch. New sketch. All right, let's go to laptop. Sketch name will be scope demo. And we're just going to do serial begin 9600. And for the moment, we're just going to tell it to, let's do this, serial begin 4 int, no. I'm just going to have it do print hello world, and then delay for 1 second. All right, save that. Arduino board. Let's see, this is an Uno. Uh-oh. Where do I change the board type? Because this is the 32-bit boards. Board options, show build folder. There's a way to change, oh, platform. Arduino IDE, Arduino, board, Uno, port, serial port, COM9, that's new. All right, let's see if that'll upload. Print, oh. I've been doing too much Python lately. Okay, while that's going, let's see. Let me catch up on chat. I saw a couple things coming in, and I haven't really paid attention lately. Let's see. Is the external crystal being used in the Arduino code? The Arduino code is based on the oscillator frequency. I'd be careful to say I would be careful to call it a crystal though, because the 328 CPU is actually using a resonator, not a crystal, for cost reasons. Is the room you live ESD installed? I have ESD mats and wrist straps, but I have a relatively humid room, so I don't worry too much about ESD, but I'm taking some precautions, just not a lot. Unplug reset plugins. Yeah, actually, one of the things I want to do, I did it for the display unit. I've already cleaned all the potentiometers in here and the connections between this module and this module, but I haven't gotten to cleaning the actual modules yet because of time, so we'll do that. Long ground is bad, lots of inductance, very bad. You're right, Sebastian. It's a terrible idea. Don't try that at home. Resetting cards fixes all kinds of issues, even gold. Yep, totally agree with DefBomb. Actually, the other thing I found was when I opened this up, I didn't pull any of the ICs out of their sockets, but I noticed that they all could use a gentle push and be reseated. And so at some point in the future, I actually want to tear this entire thing down, recap it, and then do a cleaning on all the socketed stuff, stuff like that. So we'll do that eventually. Okay. Here's what I wanted to do. Can I do a zoom? Thought there was a way to zoom. Control equals. So super complicated program, open up serial, and then constantly print hello world. And now we're going to connect up to the scope and see if it says hello world. So let's go back to this guy, disconnect so that I am free and clear from ground, and then plug this back in. And we can see something is happening. We're still on B, so let's slow down. DC coupled, yep. Wait. Okay, that's not gonna work. I have it set to 1 second, which means I would actually have to sweep at a millisecond 10 milliseconds. And yeah, okay. I didn't think that through. So let's drop this down to 100 and then re-upload that. Upload. Build done. Alligator clips on scopes are great for antennas. Frederick, we should turn that into a t-shirt. I like that. Okay, that's looking a little bit more reasonable, but we're still, let's see, what am I, let's go DC coupled, because I'm DC coupled. Still having trouble finding the trigger. I'm on B, left. Trigger mode is channel 1, no delay mode. Might still be too slow for us to see it. Let's try, yeah, that intensity is all the way up. Let me think about this for a second. So 9600 baud is, it takes 104 microseconds per bit, and Hello World has HELLO space WORLD bang LF. So I lost count. Was that 14 characters? So it'll take 1.45 milliseconds to transmit the entire message. So let's delay 3 milliseconds. Let's try that. The challenge we're having, this is a good example of digital versus analog scopes, right? The screen can only update when it sees activity, whereas a digital scope can hold the previous trace or have persistence. So if you have a really slow signal like we're doing now, it could actually take it a while before it transmits or updates. And I totally lost my train of thought while I was mucking around with this. So I'm not getting, actually I guess we're getting a stable trigger. The problem is the rise times are so fast we're not able to see them. So what if we just try to get one single bit? And I guess that's not going to work, is it? Unless I'm missing something else. I mean, it could also be that this terrible ground connection is terrible. Let me try something. Got another idea. Let's go ground. Hook this. We'll hook this up first. So what I'm doing is I'm just trying to shorten my ground my ground lead so that there's less inductance, and maybe we get a little bit better signal integrity out of this. Because I do think part of the problem is the rise time off an Arduino is relatively fast to the clock speed. Love the clicking of the analog scope. Yeah, there's nothing quite the same. All right, so we get down here. Now that's just too much noise. It may just be that it might just be the best we can do. So here I'm talking about using a digital or analog scope for hobby work, and this is terrible. By the way, I don't think it's because of the scope. I'm definitely blaming the user, not the scope. I don't want that to come off as, I don't want it to come off as the scope doesn't work. It's more likely I'm doing something really stupid at the moment. No. So there is one problem I just thought of, and I forgot to mention this before. So this is, oops. This is the probe that I'm using, or one like it. And so I have a question for you guys. What is the difference between the signal that comes in here and the signal that comes out of here? So signal comes in, signal comes out. there is a difference between these two signals. Anyone know what it is? Well, the answer is traditional analog probes like these, or traditional passive probes like these, are divide by 10. So if 1 volt goes into the probe tip, 10 millivolts comes out. And so that ends up meaning if we're looking at a 5 volt signal on here, it's really a 500 millivolt signal on the scope. Which on a digital scope isn't a big deal. They usually just do math and multiply it up so it looks like 1 volt is 1 volt, even though that's not the case. So I'm going to switch to these probes because it has a switch between by 10 and by 1. So this is going to have more loading, which isn't a big deal for this circuit. However, it will reduce the signal by less or attenuate the signal less. So we might get a better view on our scope here, because I suspect the divide by 10 is just a little bit much for what the scope can handle. And so now we should be at something like, man, that still looks terrible. Makes me wonder if something else is awry. Let's just do a quick sanity check. So we'll go to second channel, trigger on channel 2. And that's actually looking more like what I expected. So I might have an issue on channel 1 because this is more of the waveform that I was expecting to see. Now let's see if we can get our trigger to... We're still not getting a good trigger. And I'm triggering on B. Okay, this is much closer to what I was expecting to see. So there's definitely something going on with this channel. All right. But we're still not triggered. And that, what is it you're trying to do again? Good question. I thought this was going to set up a lot faster than it did, so sorry. I've got my Arduino Uno down here, and on the Uno, I just have it outputting a serial message. So we're basically trying to look at a digital signal on our scope. And one of the things I wanted to show is you end up missing the edge transitions. So you really just end up with something that looks like this, where it's basically you can see the 0 level and the high level, but not a whole lot in between. And now I think about it, that might be part of our issue, is the edge rate of our signal is so fast, the scope isn't able to trigger on it. Oh man. Increase the hold off. Yeah, that's I'm gonna try something else real quick. I think I just realized I think I know what the problem is. So let me set this up, and as it uploads, I'll explain what I'm doing. Write 1 high, digital write 1 low, and pin mode 1 output. Let's do project Arduino upload. All right, so what I've done now is I've changed my Arduino code to just do write a high, low, high, low, high, low. So the pin should just be transitioning. And if we zoom in, yeah, okay. Now I think I know what the problem is. That's a real bummer. Okay, I want to make one quick change and just make sure that it's not the module again. Level, if I AC couple it. No, I don't want to AC couple it. It needs to say DC. Okay. Digital write 1, high, low, high, low. Slow down baud rate. Actually, how can I explain this one? Let me think about something for a second. Wait, it's still not what I think it is. Channel 2 should be outputting, even divide by 10 should be fine. Digital write, high, low. Just for sanity, I'm going to change this to pin 13. So I sort of disagree about a secondhand digital scope is better than a secondhand analog scope, as I explained earlier. The one thing I don't like about old or used analog scopes is that they're very difficult to repair. And so, okay, so user error. And 13 is on. And we're still having a hard time triggering on, there we go. Am I in a chop mode? Okay, okay, now we're getting. So why didn't this work when it was on pin 1? So now I'm just going to change my code, go to pin 1. Oh, God, James. I know why. I know why that previous measurement didn't work. So previously what I was trying to do, so I just changed this back. This was 13, 13, and 13. And what I was trying to do was just toggle the pin high and low so that we could get a waveform. When I did this earlier, I was using it on pin 1 because I was trying to verify that pin 1 was actually toggling. Does anyone see a problem with trying to toggle the pin on pin 1 with this code? The problem is I left serial begin going, and so the pin was not doing anything near what I expected it to. So I've disabled that, and we're going to upload that code, and then we'll go back to my scope, plug this back in. There's also 0 delay between them. That's okay. There's an inherent delay with digital write, and so yeah, that's okay. All I wanted was something to go high and low as fast as it could. That's actually not a problem. It was by design. Now we'll plug this back. I think I was on channel 2 before, and there we go. Okay, so that's where I was trying to verify earlier. So now we are stably triggering, and we're getting 1-0 pattern. So now what I'm going to do is disable that and go back to my serial pattern, because at least now we know we should be getting something on the screen. By the way, what I was trying to verify is if we look at the rise time of this signal, I was thinking that the rise time might be so fast that the scope wasn't able to trigger on it. But by doing the 1010 pattern, now we're able to see that we're able to trigger. And so I want to point out two things. Let's do this and then move this position to here. So this waveform now takes, it starts at a high and it takes 3.2 divisions to go for a cycle to complete. So 3.2 divisions. So this is why digital scopes are better in my opinion, because now I have to say, okay, I have 3.2 divisions at 2 microseconds per division, and then inverse of that, we're getting a switching frequency of about 150 kilohertz, which is about right for digital read and write. Now, if we switched it to port manipulation, we could get that much faster, but just wanted to show that's how we measure frequency on an analog scope. Now let's, what was I going to do next? I wanted to show, let's zoom in and then come to here. All right, that's too far. That's the best we're going to be able to do at the moment. So here, if we wanted to measure the rise time of the signal, and I'll explain why I wanted to do that in just 1 second. What we would need to look at is how long does it take to transition from 10% to 90% of its rising. And so what I can actually see is we start at 1, 2, so we go 1, 2, 3 to the middle line, 4. So it takes 4/10 of a division for this to rise. Okay, so if we say 0.4 and it's 50 nanoseconds per division, this signal has a rise time of about 20 nanoseconds. And so that's important because if we do 1 over that, there is 50 megahertz of bandwidth in the edge of our signal. So even though we are only transitioning at 150 kilohertz from 1 to 0, there's still 50 megahertz of content in this signal that we have to account for. And so we already measured earlier that the scope frame can handle 50 megahertz, but that was one of my thoughts was, well, maybe the edge is so fast that the trigger circuit isn't able to see it. So why didn't the slow baud rate work? That's a great question. Since we know that 150 kilohertz works okay, I am going to actually increase the serial transmission, and we'll keep that the same. I'm gonna bump up the baud to 1152 and see what we get now. Okay, that is really close to what I was expecting. If we can get this thing to show us, oh, there we go. Okay, let's see. Let me make sure you guys can see what I can see. So here we have our 0 and our 1, and we can see our bit pattern. So 0, 1, 0, 0, 1, 0, 0, 1. As I zoom out, I can now see that the entire message takes, let's say it starts from, so go 1, 2, 3, 4, 5, 6, 7, 8 divisions at 100 microseconds per division. So it's basically, let's see, 800 microseconds. Is that right? How fast is 800 microseconds? Let's divide that by what I say. It's like 14 bits. I might have that number wrong. 800 microseconds, 14 bits, divide it. We get a speed of 57 microseconds, 17 kilohertz. Okay, I've lost track of what I'm trying to do. It's taking 800 microseconds for that to, I know what I want to do. I want, it's 115 kilobit, which is 8.9 or 8.6 nanoseconds per bit, right? 115 e to the third. So divide that, or 1 over that. So 8.6 nanoseconds. And we said it's 14 characters we're sending, so 14 times that should be 121 nanoseconds. And we're seeing, let me take it out of here. Yeah, we must be seeing repeats of the pattern. Well, that was weird. All right. Let's try. So it should be 100 nanos. So after 12 nanoseconds. So let's go down to. Okay, I've missed something. I'm missing something obvious. 115, 200. Okay. Oh my God. I'm getting tired. Okay, 115, 200. So that's our baud rate. And then our bit rate is 8.6 microseconds. We have 14 bits going. So we're getting about 121 microseconds for a message to go across. So if I had gone down to 10, we have, I can't count that. Okay. That is one complete message. So when I'm zoomed out, what is this? 100 microseconds. Why are we seeing so many bits? That's got me confused. I'm going to try something. All I'm going to change is how long we delay between messages. I want to see if this waveform changes. Uploading, done uploading. Huh. Yeah, okay. Yeah, I guess we were just seeing multiple messages. I just, it was throwing me for a loop. Yeah, anyway, 100 microseconds, there we go. Long story short, I totally take back what I said earlier. Maybe analog scopes aren't that great for hobby use because when we look at this on a digital scope, it's a heck of a lot easier to read, but whatever. It's still a badass scope. I mean, 200 megahertz. I haven't talked at all about this module. It's a differential module, which is really cool for measuring high voltages or measuring small signals on a high voltage differential. Yep, that is the correct math. Thank you. I'll share with you the mistake I was making a minute ago, and it's what was throwing me off. Is I was saying I have a bit rate of 115,000 kilohertz, and so I was off by an order of magnitude because I was actually calculating for 115 megahertz instead of 115 kilohertz. But it's cool. Let's see. I don't think I can get. Yeah, I wanted to try. Can't do that. Okay. Well, I think that's all I'm going to show on the scope. If you guys have other questions, electronics in general are okay. But if you got questions about this scope or scopes in general, we can talk about that for a few minutes. But I think I'm out of things to talk about on here because we've reached the limit of what I played with yesterday. Like I was mentioning earlier, in case you just joined, so I've been actually recording the footage of me playing with the scope. Yesterday, when I was repairing the damaged resistor, I was taking video as I went through and looked for it, cleaned it up. So I'm planning to do a full video on this particular scope, kind of like sort of like a LGR style video about technology, but instead of computers or video games, I guess he only does mostly computers. So instead of like a computer, it's going to be focused on a scope. It's actually a series I've wanted to do for about a year, and I'm just now starting to have time to do it again. Since this was such an easy repair, I figure why not turn it into a video. So in the near future, I'm planning to release more of a edited video about what the scope is, the history of it, and then show some measurements on it, just because I think it's pretty cool. What's that scope cost? So I got mine yesterday at a flea market or swap meet, or I think in the UK they're called boot sales, boot marts, boot camps, not boot camps. That's something different. I paid $100 for this scope. It was sold to me. The seller said, hey, the screen doesn't work. So I took it apart. And when I got it all taken, apart, here's what I found. This guy's video, I tell you. So when I took it apart, inside the high voltage supply was there's a diode, there's a couple of diodes, this film capacitor, and then this resistor. And at first I saw all this black gunk and I thought, oh, clearly something exploded. And in fact, somebody on Twitter, there's two people that have a similar name, so I don't want to say the wrong person. But somebody pointed out, well, maybe it's the wax in this film capacitor melted. But then I noticed that this junk is up here. So instead, I think what happened is, I think there's another fault in the scope that causes this resistor to fail. And it's been repaired before. And somebody applied conformal coating in hopes that it would help protect it or something. So I replaced that resistor. That's all I did. I mean, and I cleaned up some stuff. You know, I did some cleaning, but basically replaced that resistor and it started working again. So I'm joking that it cost me $101.45 because I had to actually go buy the resistors. I didn't have any half watt. So yeah, cool stuff. Yeah. All right. Let me think. Is there anything else that we could do? I don't think so. I don't know. Okay, I tell you what. I want to close up with one thing because I wanted to capture footage of this. So I'm going to set up a cool looking waveform that has no measurement value whatsoever. Sorry for the noise. Let's get our waveform generator, and we'll plug in a second channel. Turn this on, plug this in. All right, power you up. And then we're going to do, we're going to chop between this signal and this signal. Disconnect our Arduino. In fact, let me just get this out of the way right now. This should be fun. And then let's go over here, plug this in. Let's go, I think this might actually be set up for almost exactly how I want it. All right, so we've got that waveform going on. This channel should be probably about the same, right? Sorry. Don't you want to change the capacitor? No, actually the capacitor is fine. So if we look at the original capacitor, once I cleaned off whatever that conformal code is, you can see it's in good shape. And then once I disconnected this resistor, I effectively had it out of circuit. And so I did a couple measurements on it. I measured the I measured the leakage and its capacitance, and it's fine. It's a metallized polyester, and so because this wax seal hasn't been broken yet, it probably hasn't had too much corona or any damage to it, and so it's actually okay. I might change it if I go back and recap everything else, but certainly in the short term, I'm not too worried about that cap. It's actually doing okay. Did you find why it burned the resistor? No, not yet. I did do a couple of thermal camera images just to see if I could find if there's something else like on the board that it's connected to causing problems, but I didn't really see anything that made me too concerned. So I don't know why it's failed yet, and that worries me, because if it's failed once, it's going to fail again, in my opinion. Because of where it's at, I don't understand how it failed unless something downstream was damaged. And so it's something I'm keeping an eye on. I was actually sort of wondering during this live stream. I mean, it's been on for 2.5 hours today. I had it on for about 4 hours last night, and it's still working. So I really don't know what damaged that resistor. And like I said, as my friend pointed out, I think it's been damaged once before, or it's been repaired once before. All right, so we got that, but what I really want to do then is trigger on channel 2. Isn't that cool? And then what can we do with channel 2 now? We'll just leave it there. That's actually, well, what I don't like about that though is it sits down there for so long. What if we did a square wave? Nope, wrong channel. Yeah, we'll just leave it. Good enough. Why did the delay change? Yeah, that's pretty cool. Okay. Do you think you learn more using an analog scope? I don't know. I think you learn more about how a scope measurement is made, but I don't think you learn any more about electronics or about a circuit. So I don't know that it's super relevant to learn how to use an analog scope, but I think it's something, it's like any kind of tool. If you understand how to use any generation, then you're more comfortable using things. Like, for example, even though I never use it, I know how to use a slide rule. So I think same thing with the analog scope. Part of why I want to do this live stream is because I wouldn't normally sit down and go through and play with a scope like this, or play with a scope this much, because I'm rarely going to use it. But now I know when I use an analog scope, there's a couple of things I should keep in mind. First is we have to make sure we set the vertical scale. Well, this goes with all scopes. We have to set the vertical scale, but we have to make sure that we're using the correct vertical channel, which different scopes will have it set up differently. Like this one, we have to actually tell it which module to use. And then when we use triggering, we have to keep in mind that the trigger is what drives the electron gun. Whereas with a digital scope, triggering is what stops the acquisition. In an analog scope, triggering is what starts the acquisition. And so we just have to sort of think about how does that signal happen. The other thing that I realized while using it is when you change the trigger level, there's no indicator on screen what that level is. And so you really have to think about, okay, is my vertical channel going around or near 0 volts so that my trigger signal can actually see something occurring? It's just something I hadn't thought of. Is that from Carlson's lab? You're the wizard, not the equipment. And then with a digital scope, you're lazy and just push auto set. Yeah, you're right. However, sometimes you just want to press the button and get an answer, right? I mean, that's not the worst thing. So, all right, show a assiduous curve. I cannot, because I don't know how to do XY mode on this scope. However, my friend did send me a link from, I think Dave Jones was talking about how to do it on a 7000 series scope, 7000 series from Tech. So it's something that I'll go look into, but I don't have I don't know how to do it on this scope right now. So, all right. want to thank everybody for joining in for this live stream. It's been fun. I'm getting hungry, so I think I'm going to go eat lunch. I'm going to stick around with the chat for just a few minutes. If you want to keep the conversation going, I encourage you to join the AddOhms Discord. The easiest way to get to it is go to addohms.com/discord, and that will redirect you to an invite link so that you can get into that chat room and we can keep talking. I have 2 AddOhms videos in the works right now. In fact, I'll probably go work on one of them when I'm done. One's going to be on MOSFET measurements, we did a live stream of MOSFET measurements. One is going to be VGS thresholds for MOSFETs. So I've got a animation coming out for that. And then probably after that one, I'm going to edit this video, a video about this scope, and release that. So we got a couple of those coming. Also, don't forget, I am a presenter on Element 14 Presents. Each month I have a show called Workbench Wednesdays, where I show various things you find on your workbench. I've done a power supply, and I did a multimeter, and I've got one coming in October that talks about how to use a spectrum analyzer. So go check that out. Yeah, I should have links for all this stuff. Anyway, I'll be sticking around in the chat for a few more minutes, or come join us on Discord. My name is James. I'm the Bald Engineer. Thanks for stopping by. What is this, Anchorman? If you find these videos helpful, please consider supporting AddOhms and the Bald Engineer on Patreon.